Hi everyone, my name is Enrico Casella. Today I will be presenting this paper by the title HVAC Power Conservation through Reverse Auctions and Machine Learning. Why is this paper relevant? Well, we've all seen in the news something like this: Texas power generation failed, California heat, power outages. We've seen peak demands, peak records of power demand, and even astronomical bills. This is caused by extreme outdoor temperatures because winter storms and heat waves carry with them such as extreme cold or extreme heat. This has consequences on power outages because the grids cannot handle all the demand that is needed to heat and cool houses. As a consequence, we also have astronomical bills. We've seen in Texas $5,000 bills delivered to some users. Overall, we can see on this image that there has been a trend where blackouts due to non-weather related events has stayed pretty much constant throughout the years, going back all the way to 1984. But the weather related ones have been increasing more and more, 67% increase of blackouts since 2000 due to weather related events. And so it is clear that the high peaks of demand are associated with extreme temperatures. Specifically, the issue is that HVAC, which stands for heating, ventilation, and air conditioning, and so is basically the cooling and heating systems in our homes, is triggered, and it keeps pumping heat and cool during these events. Moreover, it has been shown that heating and cooling during 2020 represented 51% of residential consumption. During a similar event of heat wave in Texas, ERCOT, which is the entity that controls energy distribution in Texas, issued a conservation alert. Specifically on the first line here, you can see they asked users to set their thermostat to 78 degrees, saying that every degree of cooling increases energy by 6 to 8%. So it is clear that this issue is mainly the peak is mainly due to the heating or the cooling, depending on what the weather event is. Now, ERCOT in this situation gave this alert through television, through radio, through social media. But we know that nowadays we have better means to do that. We have devices that allow us to track remotely the real-time consumption. We have apps that allow us to communicate with our smart thermostat in our homes, and we can communicate as well with the utility company. And so it has been of interest of the utility company to reduce this demand, not only because of the social consequences, but because there is a big financial loss. We can see in this graph that as the quantity of electricity increases, the price of producing this electricity for the utility company starts growing exponentially over here on the right side. And so reducing this demand by a certain amount actually gives a great price reduction. It has been shown in a paper that 100 megawatts of savings under these situations equals monetary rewards that can be given to users to adjust their temperature up to 36 years. And so it is clear that there is a big interest by the utility company to do something about these peaks. And so the current solutions involve techniques such as price-based demand response, incentive-based demand response, or demand-side bidding. The problems with them is that on one side, either the engagement is too low, such as in the case of price-based demand response, because users don't simply keep up with what are their rates of using energy. And on the other side, it can be too high because the incentive-based approaches have been used so much that there is response fatigue and users don't actually keep up with all the requests that they receive. On the other side, there have been attempts to use storage for electricity, such as electrical cars and also just external storage batteries. But obviously these means cannot be pervasive because of simply of their cost. And so in this system, we try to tackle these issues and just getting engagement quite right and try to use pervasive solutions that are cheaper and easier to employ deploy on a large scale. And so this is our system overview. We have on the left side the utility company, and on the right side we have users, which are equipped with a smart energy management systems. So basically, as soon as the utility company anticipates a peak load, it asks users to submit their bids. Now, what are these bids? The bids are options of preference that the users are willing to change in their thermostat settings, specifically how many degrees would they be willing to change and how much money would they want for those options. And so at this point, given these bids, the smart energy management systems calculate through machine learning predictions what will be the power saving due to those changes. And it sends them to the utility company that through what we call a reverse auction, calculates and selects the winners of this auction. And eventually those temperature changes would be executed by the smart energy management systems in the users' houses. Now in this talk, I will focus on mainly three parts. One part is the reverse auction. The other part is the machine learning predictions. And then finally, we'll talk about a survey, an online survey that we carried out to understand how users perceive the system, but also how would they bid and interact with it. So let's start by the program formulation. We have n users. Each one of them has a certain power consumption, P1, P2, Pn. And so the total power consumption in the grid is Pt, given as the sum of all these individual power consumptions. So we want to set a power cap, which is a fraction of the total power, as we can see here. And so what we want to do is save as much power as is in between these two lines. So PS is the required power saving. Now, for each user, we have, they can submit from 0 up to MI bids. And so what is a bid? A bid is a triplet of values. We have the temperature, delta T, the temperature difference that they would be willing to set in their thermostat. We have delta P, the power saved for that change. And C, which is how much money would they want, the cost that they require from the utility company to make that change for a short amount of time. And so this is how we formulated our problem. We have the goal is to minimize the total cost from the utility company's perspective. As a consequence, because intuitively users would ask more money for a bigger temperature change, minimizing the cost also means minimizing the discomfort of the users. Then we have our decision variables constraints. We have the domain, which is a binary variable, and we also say that no more than one bid per user can win. And ultimately, we have our power saving constraint, where basically the power saved from all individual users needs to accumulate to an amount that is greater than the required power saving. And then we have a payment rule, because users are not paid exactly what they ask for. They are paid a certain amount that is stated by this payment rule. Why do we need this? The reason lies in the property of truthfulness. Truthfulness is a common property of reverse auctions. It ensures that the auction mechanism can run effectively. And what we mean by that is that it prevents users from under or overbidding, and therefore manipulate the system in such a way that they can gain money from it. And so in our paper, we prove theorem 1 that the reverse auction mechanism that we propose and the optimization problem POCO that we just formulated is truthful. Now, I won't go into too much details about how this is done, but we can definitely talk about it at the end. We also prove that POCO is individually rational, which means that each user is paid an amount that is greater than 0. It's a positive amount. And third, we also prove that our optimization problem is NP-hard. And so we need a heuristic solution. So the heuristic solution has the part about the reverse auction, which selects the winners. And there's also a part about the payment rule, which is also heuristic and needs to fulfill the property that we just mentioned. So how does this work? We have an initialization phase where we initialize the variables that are relevant, such as the output of the list of winners. MPCS, which is the value that we will keep with which we will keep track of the accumulated power saving. Then the core of the algorithm lies behind this ranking criterion R. So basically, it is the ratio between the cost that a user is asking for a change and the power saving corresponding to that. And the idea here is that we want to prioritize users who have a low cost, but a higher power saving. And this can be due to different reasons. For example, it can be that their house is so efficient that they're able to maintain a good temperature, but also save a lot of power. And so then we go through this loop where basically at first we pick the first element in the list R of the ranking criterion, which are sorted ascendingly. We take the first bid corresponding to the first element in R, and we update the cumulative power saving accordingly with the corresponding power saved, and we add this bid to the winning list. After that, all the other bids from these users are removed, and this is just to make sure that only one temperature change is executed, as we have seen in our constraints before, and then we return the list of winners. Obviously, we go through the loop until we have satisfied the power saving requirement. Payment rule, as I said before, we need to still prove those properties that we proved for the optimal solutions, such as truthfulness. The truthfulness in this case is proven slightly differently. Specifically, we adopt a theorem that states that if we can prove that the allocation algorithm algorithm 1 is monotonic, and that through the payment rule that each user is paid the critical value, which is this one here, then the grant mechanism is truthful. Again, if we want to dive into more details about how this is proven, let's talk about it at the end, or reach out to me through email. We also prove that the grant mechanism holds the property of individual rationality, so each user is paid a positive amount, and we prove the time complexity of the mechanism. Let's move now to the power saving predictions. As I said before, given a user bid, which is a triplet of delta T, delta P, and C, we need to, basically the user knows how much temperature they would change and they know how much money they want, but they don't know what is the power saving. And so the energy management systems in their homes predicts the power save that is that we have when we go from temperature T1 to temperature T2. We reviewed the current literature of how power is predicted, and most people rely on steady state approaches. So there is no change in the thermostat settings. We have a fixed thermostat settings, and the literature uses neural networks such as recurrent neural network or convolutional neural networks or deep learning, and predicts the trend of the energy consumption within a given time frame. However, the issue with this is that not only the steady state approach does not fit our needs, but also because the most accurate predictions are by deep learning, the learning rate is very low. And so we need a very big data set to make predictions. And so we need something that fits our needs, that is able to predict transient state and that is able to learn fast. So how do we do this? First of all, I want to highlight what is the difference between steady state and transient state. With a steady state, what happens is that the prediction, figuratively speaking, with this toy example, I want to show that making a prediction during temperature T1 will be equivalent to predicting this curve, this line, and during T2, this line. But what happens during the transition that is highlighted during this box? So if we want to change our temperature for, like, let's say an hour, what would happen? How would they calculate that? They would probably need to calculate each individual power consumption and calculate their difference. And that looks kind of like something like this. But what we want to do with our transient state approach is something like this, where we are able to follow the trend of the energy consumption and eventually accurately calculate the power saving. And so in order to have a wide-scale approach that can learn fast, we decided that contrarily to what the literature does, we need to just calculate what is the power saved within that time frame. We don't need a whole trend of energy consumption, we just need a number. And similarly, we need to rely on easy to obtain information. So nothing that is considering the house size or the occupancy, but something that is tangible and easy to obtain. And so we have the inside temperature, the current thermostat set point, along with the new thermostat set point, and the time of the day, plus some weather-related information. And so we tested different algorithms, performed a grid search on them to find the best parameters, and eventually we landed on the use of random forest. And here I just list a few relevant parameters about them. Survey data. So this survey was carried out in collaboration with the Psychological Science Department of Missouri Science and Technology. We built a survey with Qualtrics and distributed it with Amazon Mechanical Turk. The main questions that we asked are as follows. We asked them what would be a typical thermostat set point that they would set on a hot summer day. So let's say they say that the temperature is 70. Then we asked them, how high would you be willing to go? And let's say that they say 76. And so for each option between 70 and 76, we asked them to say how much money they want. Now, our survey results show that we have 78% of total users is willing to have at least 1 degree of change. And we also see on the right side that more or less the trend of the compensation required is linear, but there is also a lot of variability. So let's dive now into the experimental sections. Data collection. We used Energy Plus. Energy Plus is a software that allows to simulate realistic power consumption data. It is funded by the US Department of Energy, but they collaborate with all sorts of members from the industry, from national labs, and from universities. And so we can say that Energy Plus is the state-of-the-art building energy modeling engine. It's funded by the US Department of Energy, and it's tested according to the ASHRAE standard 140, which is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. We consider Energy Plus the high-fidelity energy analysis and thermal load simulation software. The very interesting thing about this is that it allows it allows the editing of very low-level details, such as the shape and size of the house, the materials used in the walls, in the window. And so it really goes deep in how you can change these models. Specifically, we use the models from Pacific Northwest National Laboratory. We collect data from June to September from Miami, Florida, which is considered a hot area. And we focus on changing 2 different parameters, foundation type and heating systems. We have 4 different values for foundation types and 2 different heating systems. And so addressing a wide variety of residential houses in the US. And we also changed the window U factor material. So we consider 5 different values that kind of like reflect how well they retain temperature inside the house. And so combining all these parameters, we have a total of 40 different models, and we used each of them twice to kind of simulate the idea that we can have similar houses within a certain geographical area. And so let's look at the power prediction results. We compare our approach with the following comparison approach, which uses similar features and has a similar easy to obtain information type of approach. And we see on the left side, we have the error percentage with respect to the data set size. And what we see is that our approach has more than 80% of samples within 5% of error, which is a great result. And on the other side, the comparison approach has terrible results simply because, as I said before, the steady state is simply not made to be predicting similar transitions. And so they have more than 80% of samples with more than 70% error. On the other side, we want to trend the learning rate of our prediction model. We show this through median error and explained variance. Explained variance is a common unit measure of regression models. The high is between 0 and 2, and the higher the score, the better the prediction. And so what we can see here is that with already just 20 samples of training set, these predictions are pretty accurate. And we need to think that the training doesn't need to necessarily be done during situations of extreme heat, but it can be made during the day or while the user is not home. Let's look at the reverse auction results. We also use a comparison approach that was published in Infocom. The difference with our approach is that they only submit one bid. And so we randomly select one bid per user, but we calculate the optimal solution for this approach. And so as we can see here, we have on the left side the objective value and on the right side the payment. We fix the power cap to 5% reduction, and we vary the percentage of participant on the x-axis. And so what we see is that the comparison approach MEDR does not do nearly as well as we do. And on the other side, we are much closer to the optimal solution. Similar thing can be said about the payment. Now, in this specific experiment, we use PK, stands for perfect knowledge. So we use the ground truth from Energy Plus. And then we also evaluated what happens when we use the power saving predictions from our machine learning model. And so because the trend is so similar, it further justified that our machine learning predictions are very accurate. Then, instead of varying the percentage of participants, we fix the participants to 60%, and we vary the percentage of reduction from 3 to 9%. And this gives similar results as we saw before. We do better than MEDR across all situations and scenarios, and we perform more closely to the optimum. So in conclusion, this work represents the first comprehensive approach to consider realistic power dynamics and considers power saving predictions while modeling realistic user bidding behavior. Speaking of behavior, our survey shows that 79% of participants are willing to participate in this project. And we see that actually that amount highly exceeds the percentage of participants that we need in our experimental scenarios. We also show how we perform by scaling our with scalability performance. And we show that our solution performs 58 and 68% closer to the optimum compared to the state of the art. We also show that our machine learning predictions are very accurate and we can learn very fast. So this is it for me. You can find me at the following address. If you have any questions, please let me know.